Last time, we learned that vector and matrix representations can make your life easier, specifically when you implement Euler integration for a complicated system involving many states. But how do we use vector and matrix notation to find analytic solutions? Let's say that we have a spring mass damper system, like this one, with 3 masses. They can all oscillate relative to each other, and I've created them by connecting parts of the slinky together. How many states would we expect? We should have 6 states total. 3 for the positions of each spring, and 3 for the velocities of each mass. This means that the vector and matrix representation would include a state vector that has 6 components, the 6 states, and a matrix that has 6 rows and 6 columns. What type of solution to the differential equation w dot equals aw do you expect? I'm hoping that at this point you're expecting an exponential solution. W of t is equal to e to the ht times w0. Keep in mind that this exponential solution is a vector because w0 is a vector. However, the exponential term itself is still just a number for any given t. If I plug this exponential into w dot equals aw, I get d dt of e to the ht w0 is equal to a times e to the ht w0. And if I take this time derivative, I get h times e to the ht times w0 is equal to a times e to the ht times w0. And the thing to note here is that h is a number. E to the ht is a number. And w0 is a vector. But on the right-hand side, a is a matrix, e to the ht is a number, and w0 is a vector. If I divide both sides by the exponential term, which is non-zero, so I know I'm allowed to, and if I note that w0 is going to be non-zero, then I find out that h times w0 is equal to a times w0. This is a special situation where a matrix A multiplying the vector w0 is the same as just multiplying that vector by h. Such a vector is called an eigenvector of A, and h is called an eigenvalue of A. If there are n states, there will always be n eigenvector-eigenvalue pairs. The nice thing about this is that you can use MATLAB or Python to calculate eigenvector-eigenvalue pairs easily. Let's go back to our spring mass damper system. So we have a wall, a spring, a damper, and a mass. And assume that the damping is reasonably high, giving us an A matrix of A equals 0, 1, minus 1, minus 3. To use an exponential solution, we need to solve A times w0 equals h times w0, so I use MATLAB to compute the eigenvectors and eigenvalues. On the left of the code output, we get one eigenvector-eigenvalue pair, and on the right, we get the other. The first eigenvector, which I'm going to write down as w01, is roughly equal to minus 0.41. The eigenvalue is h equals minus 2.6. The second eigenvector is w02 is equal to minus 2.61, and then its eigenvalue is minus 0.4. Note that I've scaled both of these to make the second component equal to 1 in each case. I can do this because any scalar multiple of an eigenvector is also an eigenvector. What does this tell us? It says that if w0 is equal to minus 0.41, then that implies that w of t is equal to e to the minus 2.6t times minus 0.41. Similarly, if I had w0 equal to the other eigenvector, then I would get the exponential with that exponent in it. Moreover, if w0 is 3 times one of these vectors, then I would just multiply that exponential solution by 3 because of superposition. Lastly, let's say that w0 is equal to minus 3, 2, and that's equal to w01 plus w02, then that would imply that W of t is equal to e to the minus 2.6t times minus 0.41 plus e to the minus 0.4t times minus 2.61. This example suggests that we should be able to compute any solution of a differential equation from the exponential solutions for each eigenvector-eigenvalue pair. And this is in fact true. What should you remember from today? Remember that vector and matrix representations are useful for computing analytical solutions, as well as Euler integration, and for complex systems including many states. And remember that eigenvectors and eigenvalues provide the means by which we compute those solutions as exponential solutions.